look at that weren't available to us on that spectral run. And so, nevertheless, we can see here we have 3 hotspots of methane released over this region where this volcano occurs. And at the same time, we measured water vapor. So notice that water vapor does not have the same distribution as the methane. Here, for example, we see very little methane. We see a lot of water vapor. This is coming off from a polar cap. Here we see at this region B2, we see very little water vapor. And also B1, but a lot with this region OA. We do see methane enhanced to both B1 and B2 and also A. A little later, this is now 2 years later, we map this region and we see an enhancement down below the Tharsis district, another volcanic district where we see enhanced methane. But over the volcanoes themselves, we see enhanced water but not enhanced methane. So we're seeing and mapping diversity in the planet in these gases in this way. And finally, the vernal equinox, which is equivalent to a spring equinox here, March 21st, we don't see any methane on the planet. There we map most of it, a few gaps. But we do see water vapor in these regions still down here, but no methane. So you're looking at immediately the evidence that Mars is variable in both methane release and also in water vapor. We can relate that to regions of the planet and their age. Here again is the combined map showing you all the data for methane and all the data for water. And now over here I'm showing you the age of these districts on Mars. Red means the first billion years of Mars history. Blue is regions where you can't see pristine surface. These are either volcanic battlefields here, or they're covered by ice fields in the polar regions. And the green area is called the Hesperian. This represents the second billion years of Mars history. And the Amazonian is the region when Mars had active volcanoes and so on. So this is interesting because it suggests that the methane is being released from areas that are ancient in the first billion years of Mars history. Okay? And not from regions where flood volcanism has cooked the surface. You can imagine if you had microbes living below the surface and you covered with hot lava, it's not so good with microbes. You're going to kill them. And if you had stored methane below the surface, it would also probably cook that and destroy it. So, additional evidence for that explanation is these stripes here, which represent a magnetic signature in the crust that was mapped to a Mars Global Surveyor. This is thought to be the signature of hot magma and so forth at a time when Mars is young. And again, our methane release regions mapped so far are found in regions of this ancient terrain, which has not been covered by this flood volcanism and so on. Well, this has to do with the geology of Mars. We won't discuss that too much, except to point out that one of the things we note is that the release often seems to correspond with deep cracks in the crust. We think that's an important clue as to how this methane is coming out and where it's being produced. We think that what's going on is these cracks basically expose rock faces on either side, like a canyon, and when sunlight strikes the south-facing slope, the equator-facing slope, that slope gets warmer, right? So ice plugs in the pores in the rock melt or vaporize, and then pent-up gases behind that rock face will escape into the atmosphere. And of course, in the other face, you look at the CDOT process until the following season, summer in the south, summer in the north. Now see, everyone here who lives in the northern hemisphere has actually seen this working in the north, right? In the winter, you drive through a road cut, and let's say the equator, the sunward-facing cut, is wet because groundwater is seeping out through pores that have lost their ice plugs. The other face is covered with icicles and frozen water, and that's just a simple explanation. So that's actually the origin of that idea. And actually, there's an important lesson in that because we have so much knowledge that we kind of don't even think about when we see it in our daily lives. But you can apply that to even these sophisticated things like searching for methane on Mars. So this is a cartoon little video that shows you what we think is happening below the surface. down to a depth of several kilometers. There's permafrost in this region, but the temperature rises with depth, and so down here the water is again liquid. And that means that if you had these regions where you could connect this region to the surface through these voids that open, then you could let those gases escape into the atmosphere at proper seasons. And this could be one way in which this methane is escaping to the surface. Okay, well, now we have to talk a little bit about how it might be generated. And one of the ways is really provided to us by evidence obtained in the gold mines of South Africa. Now, you didn't come to this talk thinking you were going to hear about gold mines in South Africa, right? You thought you were going to hear about Mars. But in fact, in those gold mines, there is a strange archaea that lives in the hot water in fractures in the rock. And when the miners drill into these drifts, into these fractures, this water comes out under high pressure. And with it comes this population of archaea, which is a microbe. That microbe lives on molecular hydrogen. It does not live on anything created by sunlight. Photosynthesis, right? There's no sunlight at 3 kilometers depth. Let's take another look at what this guy does. Okay. Go back one. Okay. So what's happening here is radioactivity from the rock, which contains uranium, splits water molecules and makes molecular hydrogen. The hydrogen and carbon dioxide are consumed by these particular microbes, and they use that to create, basically involve methane, but they then use the energy difference in that chemical reaction as their source of energy for living. So their fuel, their food, is molecular hydrogen gas and carbonate, particular CO2. And this life form actually lives below Idaho, the one in South Africa lives on sulfate hydrogen. So these could live quite happily on Mars, and they can produce these gases there. This just illustrates the mechanism that we think may be responsible for releasing this gas into the atmosphere through these forming things that open and close that seasonally and permit particles to escape into the atmosphere. Okay, so is there any evidence for this kind of thing happening? Well, yes. Here is, in fact, evidence for fresh gullies that have formed in what it looked like in 2001, this crater wall. Here's what it looked like in 2005. You can see these actual gullies forming. And so this could be a process by which they are formed. Here's one that seems to be coming from a few hundred meters below the upper edge of the crater wall. There's what looks like a closed alcove where material is flowing down the crater wall that was released from that alcove. And this could be again released by liquid water, in this case, coming down once the permafrost plugs melt. And finally, this is work that was just published in this journal Science this year. And this particular group is looking at these flows that are called linear slope flows that are coming down this crater wall. And they find that these actually are formed in early summer. And then by late summer, they have become discolored. You see some of the flows right here, the linear flows coming down this crater wall. By late summer, they are much less obvious, and it seems as though they are weathering and changing their color and their brightness and so on. Here's another region that shows these linear flows. So I think that what's happening here is that there's a layer which is releasing water perhaps into the edge of the crater wall and flowing downstream. This could be accompanied by these gases. Okay, so these are the kinds of microbes that we found on Earth that could, in fact, live on Mars quite happily. The carbonate eaters, as I call them, they produce methane, and the methane could be for other microbes what? A food, right? There are methanotrophs on Earth that use methane as their fuel, their food, and they convert that to other forms of organics. Or they could be these sulfate eaters that produce